So we were just talking about thermal expansion in one dimension. So we're going to go ahead and do an example on that. So example 13.3 states the main span of San Francisco's Golden Gate Bridge is 1,275 meters long at its coldest. The bridge is exposed to temperatures ranging from negative 15 degrees Celsius to 40 degrees Celsius. What is the change in length between these temperatures? Assume that the bridge is made entirely of steel. Okay, so let's go back and write down our equation. So change in length equals alpha times L delta T. Now I found in our textbook that alpha for steel is equal to 12 times 10 to the negative 6 over degrees Celsius. Now let me show you where that is. Let's see. We're going to go to thermal expansion. So section 13.2, sorry. And in here we have a table and it states the type of material, the coefficient of linear expansion. Okay, so that's what we're looking at, this alpha. So we have steel, so I'm going to scroll down, and this is my coefficient for steel. Okay, and that's of linear expansion. Okay, all right, so our delta L is going to be equal to our alpha that we found, 12 times 10 to the negative 6 over degrees Celsius, times our length, which is going to be 1,275 meters, times our change in temperature, okay? So our change in temperature is going to be 40 degrees Celsius minus a negative 15 degrees Celsius. Okay, so this would end up adding. Okay, so our change in temperature is actually 55 degrees Celsius. Okay? All right, and once you put this into your calculator, you get your change in length is 0.8415 meters. Okay, or about 0.842 meters. Okay, so this is your change in length. So the change in length of the Golden Gate Bridge is almost a little less than 1 meter. Okay, which is kind of crazy to think about, because 1 meter is give or take about 3 feet. Okay, not exactly, but it's about 3 feet. So that's pretty crazy when you're thinking about the expansion of that bridge. Okay, so with thermal expansion, we can also look at this in 2 dimensions and 3 dimensions. Okay, so in 2 dimensions, we are looking at small temperature changes, and that is going to be the change in the area. Okay, and that will equal to 2 times your coefficient of expansion times A, the area, times delta T. Okay, or in 3D, we would look at the change in volume as being 3 times alpha V delta T. Okay, or this coefficient of volume expansion, which is approximately 3 alpha, okay, times your velocity times delta T. Okay, so in our table here, this last column is the coefficient of volume expansion. And again, it is represented by a beta. Okay. And just to mention something about thermal stress, that's created by thermal expansion or contraction, okay? And it can be constructive or destructive, but I'm going to go ahead and give you some examples of destructive thermal stress, and that's going to be something like expanding gasoline, which ruptures a tank that it's holding it in, okay? Or something like the weathering of rocks or pavement by expansion of ice when it freezes. Okay, these are all examples of thermal stress. Okay. All right, let's move on to our next example, 13.4. It states, suppose your 60-liter steel gas tank is full of gas. So both the tank and the gasoline have a temperature of 15 degrees Celsius. Okay, so they're at thermal equilibrium. How much gas or petrol has spilled by the time they warm to 35 degrees Celsius? Okay, so using our ideas of thermal expansion in 3D, okay, we know that our delta V is equal to beta times V delta T, okay? So what we have here is we have that these two items are in thermal equilibrium, okay, and that their volume is the same, okay, since it's a full gas tank. And we want to know how much would get spilled, okay, when the gas expands due to the higher temperature, okay? So if we say the volume that's spilled, okay, that would equal to the change in volume of the gas minus the change, in volume of the steel. Okay, this is how you would set up the problem. So this is what we want to know. We want to know the spilled amount. Okay. Okay, so this would be beta of the gas or the petrol times volume times delta T minus beta of steel times V delta T. Now again, I stated that the volume remains constant, okay? Okay, not that it remains constant. The volume of the gas and the volume of the steel are equal, okay? Same thing with the change in temperature since they're at thermal equilibrium, okay? So I can rewrite this as beta gas minus beta steel times V delta T, okay? All right, and again, I can look at my chart here, and I see for steel that my coefficient of volume, beta, is 35 times 10 to the negative 6 over C, okay? And then we're looking for gasoline or petrol, which is right here, and that's going to be 950 times 10 to the negative 6 over C, okay? So let's go ahead and plug that in. We have 950 times 10 to the negative 6 minus 35 times 10 to the negative 6 times our volume, which is 60 liters, and our change in temperature. So it went from 15 degrees to 35 degrees. So our change in temperature then is 35 minus 15, right? And so that equals 20. So our change in temperature is 20 degrees Celsius. Okay, and so when you put this into your calculator, you get that your spill is 1.10 liters. Okay, so this is how much gasoline was spilled. Okay, moving on to our next example. It states, what pressure would be created in the gas tank that we just looked at if the gas increases in temperature, again, that we just looked at, without being allowed to expand? Okay, and it says assume that the bulk modulus B for gasoline is 1 times 10 to the 9th Newton per meter squared. Okay, and I have a couple of notes. I didn't talk about the bulk modulus previously, but I have the definition here. Okay, so delta V is going to equal 1 over B, or that bulk modulus, times F over A times V naught. And remember that pressure is equal to our force over an area. Okay? Okay, so we're trying to solve for pressure. So pressure equals force over area. From this equation, we can rewrite it to F over A equals what? So we're going to go ahead and rewrite this equation. It's going to be delta V over V naught times our bulk modulus B. Okay? So now our pressure is equal to this equation here. So our delta V is going to be that spill in the last equation. So that was 1.1 liters. And our starting volume was 60 liters. Okay. And our bulk modulus for gasoline is 1.0 times 10 to the 9th Newton per meters squared. Okay. So then once we plug this into our calculator, we get 1.83 times 10 to the 7th, and this is in pascals. Okay. So this is our pressure. Okay. Now I want to mention something about the ideal gas law, and this will be used over and over again. Okay, so make sure you remember this. The ideal gas law is pressure times volume equals the number of atoms or molecules in the gas times a Boltzmann constant times the absolute temperature of the gas. Okay. Again, absolute pressure of the gas times the volume it occupies equals the number of atoms or molecules in the gas times the Boltzmann's constant times the absolute temperature. Okay, and I have stated the units for all of these. Okay, or pascals, I can say as well. The in here doesn't really have units, but it would be molecules. Okay, that would be their units, because it's just saying it's some number. Okay, it's like counting. Okay, and then we want to make sure our temperature is in Kelvin. Okay, our SI unit there. And K is a Boltzmann constant, and this equals 1.38 times 10 to the negative 23 joules per Kelvin. Okay, so using this ideal gas law, we will go through a couple examples. So I'm going to go ahead and stop the video here and continue in our next video.